All right. So really getting underway for the semester. Tonight, like I said, I want to talk about the basics on really what is CAD? What is computer aided design software? Like a real starting point for this. And we're also going to go over the Fusion 360 interface since we're going to be doing that. Second half of class, we are going to discuss and start working on the first Fusion assignment, which is the very basics on designing and working on in the sketch environment and how to create three-dimensional objects from those sketches. So to get started, let's switch over. I made up a kind of work list sheet here. And again, this is all available on Blackboard for whenever you like. Yes, screen sharing. I got you. Thanks. All right, so I wrote this up, pick and pulled from a few places that definitely described it better than I was thinking. So a basic overview of like the core vocabulary, the concepts, and steps to create objects in CAD. Now, none of this is one-to-one universal. What I mean by that is all the different CAD software is going to have its own iterations on some of this vocabulary, some of the steps, and also as your skill improves or just grows rather, you're going to find different modeling examples or projects are going to take different paths. So they're not always going to be the same steps over and over because that's just not how things work. But to get started, again, what really is CAD? Computer-aided design, also known as computer-aided drafting, computer and CAD with 2Ds, computer-aided design and drafting. Essentially, it is a computer program that is all about building three-dimensional objects in a variety of different ways. It is exactly that, computer-aided design. This is developed off of older drafting techniques, which is literally drawing. It is much more of an architectural style drawing. And what I mean by that is that drafting is taking orthogonal views, which is, and we'll get into this in a minute, an orthogonal view is looking at something straight on, but not in perspective. So if you've taken a drawing class, an art class, perspective, you're going to see something, you're looking at like a square, a building, whatever. You're not looking at it straight on, but you're going to see a little bit of the side, something to that effect. You're going to see a perspective. An orthogonal view is not a real view. You are looking at something exactly only from one direction in flat 2-dimension. And what a CAD program could do is build things digitally, obviously, in 3-dimension, but you can also see through it. And we're going to discuss what that means in a minute as well. But you will be able to build things looking at it from only one direction, possibly multiple views. And that is really a traditional method of drawing or drafting. So again, the difference being drawing is you're trying to do a life drawing. You're trying to take a more artistic view. You're trying to see things as you literally see them. Drafting is from a single dimension, one-on, not actually realistic, but dimensionally accurate. And computer-aided design lets you do that in a computer. So different types of CADs, different types of CAD models. Now, Fusion 360 will let you do a lot of this in different ways, depending on either your personal approach or what the model calls for. So traditional, more of flat 2D drawing, drafting, your very basic, actually where Autodesk, the parent company of Fusion 360 comes from, is a drafting program. So 2D CAD, that is where you are drawing an object in single views in multiple directions to create a representation of a three-dimensional object. So you're using what is called wireframes. And as it says in here, there's going to be a bunch of different terminology that we're going to use that also translates into 3D models. Basically, a bunch of different types of line. Now, I don't mean like in artistic terms, like implied line or broken line or heavy line versus thin line, that sort of thing. I mean different types of lines as they are defined as, meaning that you have your basic lines, which is literally just a straight line. You have curves or arcs, which is actually a radially based line that is an actual arc off of that is going to be defined by some sort of center point and whatever, be it inches, dimensions, millimeters, that sort of thing, based around that. The program will take care of that for you. I'm just discussing what that really kind of means. There's also polylines and splines. Polylines are just literally multiple different lines connected together. And that could be one line and an arc. That can technically be a polyline, or it can be like a series of short lines to create some sort of sketch drawing. That is a polyline. There's also, as it says here, splines, or there's different types. We'll get into what that means. A spline is some kind of curved line. Now, that seems like, well, why does that need different terms? Because we're talking about these things in a programmer sense, or rather, again, as these were mathematically plotted if you were drafting and such, because what you're trying to do is build something with actual dimensions, because these drawings that you are basing these things on are intended to be the plans for making a physical object. So that means you would need to know, if you're starting from a center point, well, how far down, oops, that's supposed to be an arrow. How far down is that in inches or millimeters? How far out is that in inches or millimeters? That sort of thing. So that's why a lot of these have different terms, because they are intended to be plotted out in a drafting sense. Now, again, you don't necessarily need to know the math behind any of this or the whys. I'm simply explaining the why these have even different terms to begin with. Moving on, it's called 2.5 CAD. It's essentially this kind of drawing where you can see through a thing, because this whole thing is plotted out, but you're only supposed to be able to see it from one direction, but you want to be able to see through it. Irrelevant, don't really need to know about it. What we're going to be working with is three-dimensional CAD, 3D CAD. So in this case, you will be able to create objects in 3 dimensions that are designed around single or flat 2-dimensional things. And it really just means that you're basing something, it's a 3-dimensional object. That's really what it boils down to. So again, there's no vocabulary test in this course. This is very much just explaining some of the different information and to hopefully help it make sense. So within these 3-dimensional objects, or this 3-dimensional CAD, there's multiple different ways of modeling things. Now, the first project we're going to work with, and a lot of the semester, is going to be building solid model objects and kind of 3-dimensional wireframes. This also can refer to how you're viewing stuff. And I mean that there's different viewing options in Fusion. We'll get to it. 3D wireframe. If you've ever seen like a lot of older movies that have digital models in them, like, ooh, look at the incredible computer graphics of, like, say, let's go ahead and go with the one of the more famous ones, the Death Star in A New Hope, the original Star Wars movie. You saw that whole plotted sphere with this kind of dot in the middle, things like that. That's kind of what it looked like, high tech. That is essentially a 3D wireframe model, because if you saw it, if you recall it at all, you could see that it had a bunch of different dots arcing in, such like that. What this is trying to do is express a 3-dimensional object on a 2-dimensional plane. You're seeing it through a computer screen. It's expressing it as best it can at the time, that kind of technology, through a flat surface. And ultimately, that's one of the things that you're going to kind of have to work on developing a sense for, is all of your inputs, be it mathematical, through your keyboard, or your mouse. These are all 2-dimensional inputs. You're trying to create a 3-dimensional object. So anything short of like virtual reality and goggles and wands, where you can actually move through space and grab and pull and twist and all this stuff, like actually, I would say physically, but virtually interact with an object, It's all going to be flat. So it's kind of a weird mental hurdle to get over, but as we start playing with it, it'll make more sense. Anyway, moving beyond that, what we're actually more going to be working with is the second one here. Surface models we're going to get to more toward the end of the semester, because that's more of a advanced way of working, because in wireframe, which is, like I said, more of like these basic shapes here, but you're really focusing just on those wire edges. It looks, if it were to be expressed through like a physical medium, it'd be wires, because that's a line in space. You're seeing this in 3 dimensions, so you can also see through it. That is not a good expression. Surface modeling is essentially a method of creating objects based on this information and filling in the sides to create a surface. Surface modeling is, think of it in terms of like a sheet of paper. You've got a sheet of paper. Thought I had one right there. There it is. You've got a sheet of paper that can bend, curve, fold, flex, whatever. But unlike a sheet of paper, you can also stretch and shrink and move this around. But the reason it's called surface modeling, it's a surface thick. That's it. There's not an object like solid reference behind it. Like if I was making a cylinder, this would be something more like a cylinder. This is an enclosed solid object. Surface, to model that, would be rolling or creating a rolled surface that essentially it only exists in the virtual environment as an outside and inside. There's nothing actually in there. So we'll get to that. I know that's kind of a bit of a head scratcher way of describing it, but also that's essentially what it is. What we're going to be working with pretty much right out of the bat is solid models. You're going to be creating an object that virtually is in fact solid, meaning that like a chunk of wood that you then had to drill into to create a hole in, something to that effect. That's kind of how we're building and we're doing a lot of modeling. It's a solid virtual object that you have to augment to change. It's not, it does in fact have, in a virtual sense, mass inside of it. It's not a direct one-to-one, but that's the best way I can describe it, especially for anybody that's not as familiar with. So like it says, unlike that, they essentially have weight, volume, and density properties. That is something that can be expressed in a more advanced method, meaning like if you were trying to express it, this is a aluminum block versus wood or something like that, you can actually, we're not going to get into this, but you can actually define that as like solid object materials so that that can be brought into like a manufacturing sense, to where it can be brought into like, say like CAM, which is computer aided manufacturing, brought into a CNC environment, and it can be made out of a material, and the program will know that it needs to use this kind of cutter at this kind of speed, at this kind of feed to cut through aluminum versus cast iron or plastic or blah, blah, blah. So that's not stuff we're going to really deal with, but just know that that's kind of where that is. All right, well, let's expand on that a little bit more. So how to go about actually doing this kind of stuff. And there's a few redundancies in this because they kind of are explained in different ways. But the best way I can say this, and what we're going to start with, are a combination of things. But you have 2 basic methods, and different programs treat this differently. If you've heard a lot of free programs, like things like Tinkercad and SketchUp, because they are cheaper or free, they're not going to have the capabilities to create like surface models and things like that. You're going to be working with what's called object-based modeling, and those would be altering provided geometric shapes like spheres and cubes and rectangles and toroids, which are donuts, things like that, and basically manipulating those by either intersecting them. Like if I wanted to make a different shape out of this, I could make a second shape that is like, say, a Tetris square, and within that I could delete that whole section, and now I would have, where's that link up to? I forgot a line. There we go. That makes more sense. I could delete sections off of that. And that's how you would manipulate things. Oops. There we go. So you'd have predetermined shapes. You can create other shapes, delete or add to them, that sort of thing. You can do that in Fusion 360. The other type of modeling is parametric modeling. Big word for a pretty simple way, big word for a pretty simple concept. Parametric modeling is creating models based off of drawings. So if I originally had wanted to make something like this, I could have made a drawing that was going, whoops, two-dimensionally, like a draft or in drafting, that would have been more of that shape already, extruded that out, which if you've ever played with, like, you know, the Play-Doh shaping toys or anything where you squeeze stuff through different shapes, that's extruding. That's taking a profile, pushing material through to create a three-dimensional object. So with that, squish material or pull material out, however you want to describe it, that then becomes an extruded shape. So I've started with basically a sketch, a drafted object drawing, and extruded that into a three-dimensional object. That sounds like it's very much the same. But in parametric modeling, say I made this side 3 inches tall, that's 2 inches, and I want to make that side 3 inches, and yada, yada, you get the idea. If I made this by object-based modeling, one of the things about it is there is no real recording history in that. The only way to go back and forth in object-based modeling is like Command or Control Z, Command and Control Y, back and forth direct modeling. With parametric modeling, I could go back and say, oh, you know what? For the part that I need, for the thing that I want, I actually needed this to have been 5 by 5, and I can leave that 2. It will, the computer, the program, will recalculate the whole thing, move this let me use a different color. We'll recalculate the whole thing, stretch these features up, keep those same dimensions there. Oh, that's right. That was much further out. Recalculate the whole thing as you need it to be without you having to like make a whole new thing. So the difference being object-based modeling, you're taking pre-made shapes and you can define the size of those shapes, stuff like that. You can manipulate objects, basically come out with the same result. But if you needed to make changes, you would essentially have to start from scratch, start all over. Parametric modeling, very similar approach. I still want the same object. However, but because this is numerically put in, I defined this sketch, this drawing, this drafted image, this drafted two-dimensional image with dimensions. I can change those around. The program will recalculate and change everything for me. So it's a really effective method. Neither is wrong. Either can be used to create a lot of different things, but parametric modeling can be a great help in prototyping, stuff like that, which is what CAD and especially 3D printing is really developed for, because 3D printed objects, they're not really meant to be like production models. They're meant to be test pieces. So it's a fantastic method of testing objects, testing designs for production, redrawing them or recreating them without having to redraw every time, making new iterations. I can just change the size, it rescales everything, recalculates everything. I can take that to a 3D printer, pop out a testable physical object, then I can take it on to a full production manufacturing. So that's kind of that's the basic essential difference between, say, like object-based modeling, parametric modeling. So the end result, both of these creates a solid object. Like I said, solid modeling, solid object. It's basically there. Surface modeling is really for more organic sculptural shapes, things with a lot more curves, a lot more rounded surfaces that are not as easy to define numerically, like plotted out on a grid. Surface modeling objects can be created by combining different surfaces, again, like sheets of paper, stuff like that, and manipulating them, joining those all together, and then the end result would still be a solid in virtual space object. You just go about it a whole different way. So again, all of this stuff can be combined to create complex objects. You could then later add like things like moving parts, surface colors and textures, imported model objects, things like screws and bolts and things like that, to basically recreate whatever you want. And that's really where it goes. That's really the base. That's really the kind of sort of basics on that. So where do you start with making a model? Like, all right, this is assuming it's like, all right, I know my way around the program. What do I do? How do I really get underway? So you kind of have to decide how you want to go about the object by choose a path. Like I said, they're not always going to be the same path. There's not a wrong way to do stuff, but there are more effective ways to do things. So again, this kind of gets redundant here. I just broke this down into what I already described as direct object modeling. You're beginning with pre-made virtual objects. You can alter and combine them. It's more a step-by-step building a model from start to finish, really linearly, and there's no real reliable way to alter past steps. Parametric modeling, it's much more of history reference modeling. Like I said, you can go back and forth in like a timeline. We're going to talk about that. It's much more based off of numeric inputs, dimensions, and your sketches, your drawings. I'm going to start referring more to sketches versus drawings, because in both drafting terms and in Fusion 360, the two-dimensional drawings you create are called sketches. Drawings refer to the full printout that you would then hand to a manufacturer, fabricator to create based on your drawings. So that's the difference, but for now, we're going to kind of use them interchangeably. A complex, and again with parametric modeling, a complex model can be altered at any point in the modeling process, so you could jump around in your timeline, and you could also make alterations that aren't just like resizing. You could add steps into, or you might find sometimes you're going to have to actually change the order of steps because some things interfere with one another. That's just one of the things that both is beneficial and also sometimes a real pain in the ass. But you'll learn that, or you'll start to learn where you can really play with that. Excuse me, sorry. And like I said, Fusion 360 really combines all of these options. All right, so just some basics. You might have heard these terms before, different file types. Now, of course, what's not listed on here is Fusion 360 files, because as we're going to get into, you can save things locally on your computer, but Fusion 360 has a cloud storage-based saving system, file saving system. What that means is you will have like referential backups on your computer, and they are dedicated Fusion 360 files, but the main storage system is virtual, and it's on a cloud server. So what that means is you can sign into any computer and have access automatically to all your stuff. So you don't have to carry around like a thumb drive or something like that. But you will, in order to 3D print stuff, need to export those files from Fusion 360 or whatever your software is to one of these types of files. So the basic and the actual oldest type is an STL file that refers to a stereolithogram. And we're going to get into how that functions in a 3D printer, but a stereolithogram is essentially a way to see all of these things in a bunch of different slices. But essentially, the other thing is it's also the least complex type. It does not store any physical traits, things like color of the object, material if that's important, surface textures, because some surface textures are not physically modeled. It's more of like it is still a physical or a virtually physical texture, but it's more something that's applied to the surface rather than like you actually going in and modeling in like bumps or things like that. Anyway, all those kind of attributes are not kept and stored in a STL file. So it's a very basic, very simplified storage system. An object file, an OBJ file, can approximate geometry, so these kind of dimensions, based off of really what is required without blowing up the file size. What I mean by that, you're not going to hope, the intention is to still have a slightly more compressed file size, so you don't have a fairly simple model or even more complex model that's like multiple gig sized. The idea is it's still trying to simplify geometries. It's still trying to simplify some information. It can hold on to some colors, some textures within the model, but it's not overly complex. So it's still trying to use that. Now, those first two, most every printer will use. The next type is a step file. This is a different type really entirely, and this is much more of like an actual like drafting 2D CAD style file, but it is essentially a wireframe file. So it will not hold on to any surface information at all, meaning it doesn't even express or save your object as a physical, again, virtually physical object. It's not a solid, it's a wireframe. It really has no surfaces or anything like that. But the reason for that is because it's really a drawing file. It's meant to be expressed in multiple views as flat 2D objects. And the whole thing is it's very clever with the naming acronym for Standard Exchange of Product Data. Wonderfully industrially vague. Now, the newest type, and this isn't always found in everything, and not everything supports this file type, but the newest type, because an STL being a very, like I said, the oldest and most basic, it was developed in the 80s. It's a bit old information. Like I said, it can't capture a lot of stuff that like a lot of computer modeling, be it for CAD software, for your more sculptural software, stuff like that. None of that stuff can be retained. So a lot of manufacturers and open source software engineers, stuff like that, got together and basically team developed a file type that is called a 3MF, 3D manufacturing format. You've got to see where that's going. And that is used by basically any new application and 3D printer. The whole goal there is so those would actually communicate on the same level and without like weird hiccups and glitches and such, or at least trying to minimize those. That file type will hold all kinds of geometries, physical information of the model, color, texture, yada, yada, yada. And again, the goal also is so it doesn't end up being like a humongously sized file. So those are the three main file types that work back and forth between your CAD software and 3D printers, as well as a lot of other manufacturing types, but we're not really going to get into any of that just yet. All right. So the next part I want to talk about is just to give you an idea of really the steps or some different versions of steps that you might go about in creating an object. Like I said, CAD design models are not made the same way that you would fabricate something. Like if you go out and try to make a, I don't know, wooden toy, you'd start with like a single brick, maybe cut into that, then you'd add stuff, something like that, drill holes, that sort. A lot of that stuff really does help inform the way you would make something, but at the same time, a lot of stuff gets recreated, or rather you will create stuff in CAD software, basically and ideally letting the program do the work for you. You have what you want to do. There's obviously ways and you're going to have to manipulate it with certain tools and such, but the idea also being that you're going to let the tool of the program do the bulk of the work for you. What I mean by that is some models are created with basic shapes, like I just said. They can be trimmed down, added to like object-based modeling. You can either start with a predefined sketch or which would be parametric modeling, or you could start with a object-driven, starting with an object. So like here, The hammerhead starts as a basic sketch, this profile of the kind of block with a V cut in it. Then it gets extruded. You can extrude in one direction, both directions, or symmetrically, that's probably done here. Then to make to make those cuts, because some of this, and you can see it's called a revolve cut. We'll get into all this. You have to worry about the terminology yet. But essentially, what it's hard to see through this 2D medium without being able to actually have the object in the program and be able to like look at it from multiple views, tumble it around and see. The bottom here is cut straight across, so that's flat. The top here is a compound cut, so it's cut in multiple directions to make the surface domed and the bottom of the claw straight through. So obviously, if you were going to like make that in real life, you'd cut a block, probably take it to a sander and roll it around, all of that, and then cut it to like a bandsaw and cut out that chunk to the bottom, that sort. In CAD software, like I said, the extruded cut would just be like an extrusion, chop a chunk out. The other one is a couple of operation cuts in making a compound curved surface, compound curve being so that it curves in more than one direction at once to make that dome top. Then you could add to it by adding either stacking a couple of different cylinders, or in this case, they revolve, which is taking a profile and rather than extruding it directly, they take that profile, rotate it around an axis. Sorry, we're going to get into how that all actually works and such. Basically, it's creating a round object on a profile versus extruding, which is usually like a kind of square object or a cubical object rather. And then final steps would be like adding surface colors, textures, in this case called rendering. That is adding not just color, but a material. So in this case, it'd be like applying a steel color or surface. I keep using interchangeably color and surface because in just basic rendering, you're just making it look like the thing it looks like. Like if you're making it look like metal, not just silver as like a color, but it looks like it's made of, in this case, like steel or cast iron, something like that. Other ways would be like, similarly, you would start with like a basic object already, like somewhat object-based beginning, starting with a cylinder. You can define the dimensions, meaning how tall, how wide, how tall is it, what's the radius, that sort. And then defining the sketch profile, rotating around, chopping a section away, adding chunks. But like I said, let the program do the work. You wouldn't make all of these fins individually. You wouldn't make all these holes individually. You'd make one of those fins, rotate copies around the center axis to make multiples of the same. Same thing with the hole. You'd make one hole, make multiple copies in equidistant. Thing about like CAD software is you don't have to draw out or mathematically work out the location of all of those holes. You can let the program do the work for you. So that's why I mean, but some things are very similar to how you would actually maybe go about building something. Some of these are going to be very similar, one set of steps to the other, but there's going to be variations which create very different results. Building off of those, you can make much more complex things, but like in life, like in most things, I don't know, I'm not trying to work in life lessons. I don't know why I started that way. You start with something basically simple. You keep adding simple steps, let the program do the work. You end up with a very complex finished product or finished result, rather. Like in this case, simple sketches are rotated around an axis, revolved around an axis to create a solid object with a custom profile. Then you can cut sections out. You can create these one single set of spokes. Use a tool to rotate copies around that same center axis, join them all together, and then add little features like rounded corners, which is called a fillet. We'll get into that. Fillets are engineering or drafting terms. It's a curve across what was a cornered surface. A fillet is of fish. So fillets and holes are added to fine tune and make finishing features to create this wheel hub. So you can see just some basic steps on how you go about doing that. Now, as with any of these, is that the only way to do it? Not at all. Is that the right way to do it? It's a way to do it. So a lot of the things we're going to be doing this semester it's not necessarily a correct way. It is a good way to do it. There are other ways, but this course is developed, or at least I try to, as a reasonable way of setting things up, starting from scratch, starting from sketches, building up to more complex surface modeling, things like that. So those are the basics, and there's just some links of just some reference stuff. So those are the basics on really how to start, where to start, how to start considering modeling objects, and just kind of the general basics. We're going to get into the actual history of and a lot more of the more intricacies, but that's really the basics of just what CAD modeling is, or CAD software is, how to go about it, how to consider it a little bit, at least to put it in a mental framework for you, and just some of the steps that hopefully clarify how you'd go about actually building something. So hopefully that helps. No, oops, stop.